any unexpected maintenance operation or vehicle downtime can cost you. In years past, unexplainable problems such as clutch damper spring failures, worn or broken transmission input shafts, worn or broken synchronizer pins, and premature U-joint wear were often attributed to material problems. It is now known that many of these types of drivetrain failures can occur in components that exceed manufacturer specifications for strength and quality. Spicer has created this video learning tool to educate the trucking industry on the potential hazards of drivetrain torsional vibrations and the advantages of speccing soft rate dampers. The importance of vibration management has grown dramatically over the past few years as the push for longer drivetrain life and reduced vibration continues. Spicer strongly recommends the use of soft rate dampers for all vehicles over 1,000 pound-foot of engine torque. These soft dampers are extremely important, not only to protect the clutch from damaging torsional vibrations, but also to protect the rest of the drivetrain. The words torque or torsion refer to the twisting force exerted on a component. Imagine grasping a soda straw in both hands and twisting one end of the straw while holding the other end still. The more twist applied to the straw, the more the straw deflects or winds up. Torque is being applied to the straw. By twisting the straw from side to side, a torsional vibration is being created within the straw. The same principle applies to a truck drivetrain. The engine piston's up and down motion is transmitted through the crankshaft, creating a torque at the flywheel. The friction pads on the clutch disc transmit torque to the clutch disc springs. These springs compress and consequently transmit torque to the transmission input shaft. The job of the transmission is to reduce the speed and increase the torque from the engine. From there, the engine power is carried down through the drive shaft and U-joints to the drive axle. The axle again slows down the speed of the rotation and increases torque to drive the tires and propel the vehicle. Anytime the power from the engine, clear through to the tires, is not completely uniform, there is torsional vibration. All vehicles have some form of torsional vibration. The two most common sources of vibration are, first, naturally occurring power pulses from the engine, and second, incorrect U-joint operating angles. The torsional vibrations from the engine occur due to the regular firing of each cylinder. These power pulses cause fluctuating engine flywheel speed. These small speed fluctuations are not noticeable to the naked eye or to normal engine monitoring equipment, such as the tachometer. However, by using special monitoring equipment and viewing through an oscilloscope, flywheel speed fluctuations can be studied. Fluctuating speeds are common in all engines. The second source of drivetrain vibration comes from incorrect U-joint operating angles. This model, developed by Spicer engineers, demonstrates what happens to power when transmitted through a drive shaft. Here, the U-joint is set up with correct working angles. The motion from the motor is evenly transmitted through the U-joint and drive shaft with no fluctuations in speed. But when U-joint angles do not cancel each other out, even though the speed of the electric motor is smooth, the output through the drive shaft is erratic. U-joint operating angles can change by adjusting the ride height of some air ride suspensions and also by applying load to the drive axle. It is imperative that the U-joint operating angles not be altered from the original equipment specs. No clutch or driveline damper can remove excessive vibrations caused by poor U-joint angles. There is another form of vibration that can occur from a drivetrain component being out of balance. Technically speaking, this is not a torsional vibration, but is often mistaken for one. Generally, an out-of-balance vibration can be felt and made worse by increasing the RPM of the component. The best remedy for this type of behavior is to replace it with a factory-spec component. Torsional vibrations are damaging when they strain or exceed the strength limit of the drivetrain components. Under normal circumstances, torsional vibrations don't pose a problem for drivetrain components. However, when vibrations occur at a certain frequency called resonance, their effect can be very damaging. Everything that vibrates in torsion or in an up and down motion has a natural frequency. A famous example of this type of vibration is the Tacoma Narrows Bridge. The vibration of the bridge due to the wind was not fully taken into account when the bridge opened in 1940. So when the wind direction and speed were just right, a vibration occurred which matched the natural frequency of the bridge, which resulted in destruction. When the frequency of an external force, like an engine, coincides with the natural frequency of the drivetrain system, a condition known as resonance occurs. At resonance, the magnitude of the vibrations grows and grows until something gives. Like the Tacoma Narrows Bridge, this is what happens when sound waves coincide with the natural frequency of this wine glass. It breaks. Although a drivetrain is not made of glass, it does vibrate, and it does have a natural frequency that can resonate and break. Over the past few years, government and industry pressures have made demands on the engine manufacturers to develop more fuel-efficient, cleaner-burning engines. The engine manufacturer's solution to these requirements was to add electronic fuel delivery systems and slow the normal engine operating RPM. However, engine peak horsepower has also steadily increased at an average rate of 8 horsepower per year. What this means is that modern engines are working much harder at lower RPM than older engines. Unfortunately, the cost of these improvements is an increase of the fluctuating flywheel speeds we discussed earlier. The best way to avoid damaging resonance is to change the natural frequency of the drivetrain. The most cost-effective way to change the natural frequency is to use soft rate dampers. Here we see a graph showing the stiffness of a standard damper versus a soft rate damper. The soft rate damper is considerably different from a standard damper, meaning a much lower drivetrain natural frequency, lower than the engine firing frequency, and below the normal operating range. With electronic controls on today's engines, it is now common to comfortably operate in the 1100 to 1800 RPM range, and in some cases, even slower. This graph illustrates where the peak torsional vibration level occurs in a particular truck with a standard damper. The left scale indicates how large the vibrations are, while the bottom scale indicates engine speed. Notice the spike is in a different location for each gear. This vehicle has several torque spikes in the operating range between 1200 and 1800 RPM. The torque spikes are actually above the mean torque the engine would be producing, which can cause significant damage. Now, here is an effective torsional treatment. With a soft rate damper, not only are torsional spikes much lower, but the spikes have also been moved to the left, out of the operating range of the engine. This large reduction in torsionals, combined with the shift out of the operating range, will protect the longevity of the entire drivetrain. Spicer requires the use of soft rate dampers for all single drive vehicles with peak engine torque of 1,000 pound-foot or more. Spicer recommends the use of soft rate dampers for tandem axle vehicles with peak engine torque rating of 1,000 pound-foot or more. Not only does Spicer strongly believe that soft rate dampers are the most effective solutions to damaging vibrations, but so do other heavy-duty component manufacturers.
Eaton began investigating new failure modes that had greatly increased in a very short period of time. The failures that led to this development were clutch spring breakage, transmission input shaft breakage, gear tooth breakage, sliding clutch breakage, and spline wear in heavy-duty transmissions. We also encountered synchronizer ring breakage in medium-duty synchronized transmissions. We found these failures were the direct result of engine-excited torsional vibrations. The solution was to install clutches with the soft rate damper, which included the Spicer 7 spring and Spicer VCT 6 spring. Installation of these dampers virtually eliminated damaging torsional vibration levels and subsequent failures. With the results we have achieved, there is absolutely no doubt that the soft rate dampers are a must as standard equipment throughout the trucking industry for heavy and medium duty trucks.
Spicer has 50 years of experience in developing clutches. Spicer has invested millions of dollars in test equipment and in 1985 introduced the industry's first soft-rate heavy-duty damper. Spicer Clutch uses a three-sided analysis loop to fully understand and resolve torsional problems. The loop is comprised of computer simulations, vehicle vibration measurement, laboratory testing. First, there is Toran, a sophisticated computer model simulation tool designed and used only by Spicer to predict a vehicle's vibration activity. Spicer has worked with the engine and component manufacturers to create a library of the mass elastic properties of virtually all of the popular heavy-duty engines, transmissions, drive shafts, and axles. Toran uses this data to create a complete driveline mathematically. It then determines the natural frequency of the drivetrain and predicts vibration activity in any selected transmission gear. The advantages of the Toran analysis are, first, it allows Spicer to predict vibration in a vehicle before it is built. This enables Spicer to engineer precise dampening characteristics to avoid damaging torsional vibrations. And secondly, it allows Spicer to troubleshoot field complaints and provide instantaneous calculations on vibration activity, allowing for quick clutch solutions. The second phase of Spicer's technology loop involves vehicle vibration measurements. Spicer instruments a truck's drivetrain and measures vibratory activity. These measurements are taken to verify the Toran computer model and to depict conditions in real-world situations. To complete the three-sided technology loop, Spicer employs a variety of laboratory test equipment. Data taken from the field is fed into Spicer's engine torsional simulator to reproduce the most severe conditions. Spicer's engine simulator has the unique ability to load a test damper, duplicating the exact loads it would experience in the field. All of this laboratory testing supports Spicer's capability to produce damper systems that are reliable and have the ability to extend the longevity of the entire drivetrain. Spicer produces two families of soft-rate heavy-duty dampers. For engines with torque up to 1,700 pound-foot, there is the Spicer soft-rate 7-spring damper. The advanced 7-spring features a high-tensile spring wire, a controlled hysteresis device, and heavy-gauge steel spring covers. For 4-cylinder diesels, Spicer has a special version of the 7-spring. For the most demanding applications, and for all applications above 1,700 pound-foot, Spicer has introduced a new family member, Vibration Control Technology, or VCT soft-rate dampers. VCT dampers have a low spring rate to move the driveline natural frequency below engine firing frequency and minimize drivetrain vibration. VCT dampers have the torque capacity to accommodate engines up to 2,050 pound-foot, an industry first. The VCT features hardened steel pivoting spring end caps, unique damper covers that virtually eliminate spring pocket wear, external stop system for improved overload protection. Spicer has added 2 additional friction facings per disc side for longer wear life reduced flywheel wear, and improved engagement. Unlike other soft-rate clutch dampers, VCTs ride on a common splined hub. Because of this common hub design, VCT discs are completely symmetrical. This means that the discs cannot be installed backward, eliminating the chance of improper installation. With today's stronger, lower-speed electronic engines, severe torsional vibration within a vehicle's drivetrain has become more evident. With Spicer's experience and technology, Spicer has been able to foster the development of the most innovative damper designs in the market. Combining Spicer's state-of-the-art testing equipment and expertise, Spicer has engineered soft-rate dampers to tune drive lines, preventing damaging torsional vibrations, thus extending drivetrain component life. Spicer has demonstrated that soft-rate dampers like the 7-spring and VCT are the most effective solution to reduce vibration failures. Spicer's soft-rate dampers are available on 15.5-inch Easy Pedal Plus clutches and Spicer Solo heavy-duty adjustment-free clutches. For more information about other Spicer products, such as Spicer Life Series drive shafts, Spicer Gold Series S400S tandem axles, Spicer ProShift transmissions, or an entire Spicer system, call the Spicer support line at 1-800-666-8688. For immediate product information, call 1-888-675-SFAX or visit us on the web.
Spicer is a division of Dana Corporation.